Welcome back to ECE 470 Introduction to Robotics. So in our last video segment, we talked about what is a robot, and we come out with a very relevant definition of what a robot is for this course, ECE 470. So if you recall, a robot is nothing but um, an agent or a machine that is designed to complete a task while interacting with the environment in our context of Introduction to Robotics course. So this actually helps us to further establish the kind of subject that is relevant to this course. So basically we're going to talk about the scope of robotics in this course. And when we talk about the agent that is designed to complete tasks while interacting with the environment, that machine that you would like to develop should have the ability of sensing, perceiving, planning, and acting. Not necessarily fully autonomous. It can be semi-autonomous. It can be collaborative in nature. Okay, so a collaborative robot is something that is widely studied today. A robot doesn't have to be the one doing the work itself. It can collaborate with a human user. Okay, so they can work alongside together, which is something that is fairly recent. In the past, most of the industrial robot are actually left isolated in the production line without too much physical interaction with a human being during the operation itself for safety reason. Okay, so we see that today robot has evolved into something more sophisticated. Okay, so it becomes more important to also consider the interaction with the environment because of a lot of other safety issues that we will be looking at. So in order to equip our machine with the ability of sensing, perceiving, and planning, and that include acting on the environment, we need to look at a few different aspects that is important. And so that is what you're going to see in this course. You're going to be able to understand the mechanics of the subject of robotics, so that will help you to better design the mechanism. Okay, and you will need to understand the sensory and actuation system. Okay, how the robot sense the environment and act on the environment. And of course, that is not enough because in order to achieve a desired outcome, you need to have some form of control mechanism. Okay, usually that comes in the form of being able to sense the environment and feedback into the robotic system such that it carry out certain action to achieve the goal, right? And so if we go deeper, we will know that you will need to be able to, the machine that we design will need to be able to perceive the environment, okay? To be able to perceive the environment, understanding what is happening in the surrounding, and execute the plan. Okay, so planning part is also important. The planning of the path that the robot should take, the trajectory of the joint that the robot should execute. Okay, so as to achieve the desired goal. So all this will be what you're going to learn in this course, Introduction to Robotics. And so in fact, in our first video segment, we kind of talk about how this course can be structured into three main topics, okay? But here I will not go too much into detail. We will actually talk more during the live session. So I will leave you to take a look at the three main topics, how it is being structured, and some of the terms, the spatial representation, homogeneous transformation, they might be, they might not sound familiar to you, but don't get too worried about it. We will actually go into detail as we go to the topic itself. So for now, you just need to understand that there are systematic way of representing the position orientation of the body of a rigid body in 3D space, and how it changes, the change in the position orientation, that is the transformation, using very systematic uh, coordinate system. All right. So after that, you will be able to do your forward and inverse kinematics and analysis of the mechanism. Right. So of course, it is also important, as we mentioned earlier on, to understand the dynamical environment that the robot is working in. So the interaction may change over time. There's a lot of aspects that need to be considered. Not just the planning itself. You also need to look at the control mechanism, okay, that will achieve the desired outcome, because planning itself may not always work if there are sensor uncertainty, there are there are disturbance from the environment or the surrounding. So all this require you to have or design a control scheme that would take in sense information and act on the environment accordingly. And then the more practical, or rather a more applicable topic in robot vision, we'll actually look at the science and engineering of image formation, processing, and analysis. You will understand the camera model, how you actually use a camera to help the robot to perceive, to understand what is happening in the surrounding, okay, and to do vision based control, that is to apply your visual information to control the robot and achieve certain tasks. So these are image guided robotics that you will learn in the last 4 weeks of this course. So we have prepared a few examples for this course. Here, what I'm going to do is to give you a very quick overview, not too much in depth, about some of these examples that show a lot of relevance to what we are going to study in the next 15 weeks. Okay. Um, of course, I will just give you a very quick preview of some of these examples, and then we will use them as very good motivational example to why we want to study certain topics when we go into the topic itself. Right now, we have a few examples. One of them is related to kinematics, of course. That is the first thing that you're going to study in week 1 and the next 3 weeks as well, the coming next 3 weeks. So take example the manipulator arm, which is something that is very established in the subject of robotics. You want to understand how the manipulator arm can be analyzed. Okay, so in this case, for those who are not familiar yet with how the mechanics of multi-body. Okay, you don't have to worry, because I understand that most of you come from ECE and EE. So on this part, we're going to go through them in detail when we go into the topic. But what you see here, there are multiple linkage. Okay, so all these are called linkage. Okay, and of course you have join. So all these are joins. Okay, and so we want to establish a way in representing this multiple body in 3D space. Okay, be able to represent the position and orientation, be able to explain the transformation. Okay, and one very good example in surgical robotics is a manipulator that hold on to a surgical tools. And in this case, it's actually holding on to a camera, an endoscopic camera. Okay, so this is basically an endoscope. Course with camera function that help to see what is inside the patient. Okay, so this is what is inside the patient. This is actually the abdominal cavity. Okay, so you don't have to cut open the abdominal of the patient. The tummy of the patient, you just need to insert this camera through a hole, okay, and you can image what is inside. And so because this camera is constrained to a point, so you need to understand the workspace requirement, uh, analyzing it in a systematic way. That is a kinematic analysis of the task, and that will actually help you to do your design specification. So the schematic that you see here is something that you're going to learn how to represent the multi-body system or your mechanism in this form of schematic. So don't worry if you can't understand this at this point of time. Okay, you're not expected to know them before the course, of course. But of course, for those who have worked in robotics project, you probably can appreciate what this schematic is trying to describe. And so with that, you are better equipped with the ability to design your manipulator that holds on to this camera. Okay. So apart from the kinematics, understanding how the robot can be represented in 3D space, how the change in position and orientation can also be represented in a systematic coordinate system or method. Uh, we also need to understand how it interact with the environment. So a lot of dynamics can be involved in this case, which uh, we as human beings often take for granted. The way we interact with the environment. Sometimes when we run or simply walk, it is actually a very dynamical process that took engineers many years to understand how to program them in a robot or artificially in what we call bipedal robot. And in this case, what you see, this is actually a legged robot. Okay, in this case, it is a four-legged robot. Okay, four-legged robot or quadrupedal robot. So there's a lot of dynamic involved in it, but for a cheetah or other animal that can run like this, they do not necessarily need to have the knowledge to do this kind of dynamic computation, but they can do it, execute it in a very graceful manner. So how is this done? There's a lot of science in this. So for us to be able to design robot that can accomplish some of these tasks, which is seemingly very simple in nature, in the example of nature, uh, it is it will take us some understanding or knowledge to be able to uh, do this. And even till today, our understanding of some of this dynamical process on how a living organism, including ourselves as a human being, execute motion, uh, the entire process of locomotion is still a very challenging research. And of course, planning is something that is important because a lot of time robot is really good at executing precise plan. Okay, and so in a case where we are able to integrate um, external information from things like imaging technology. In this case, this is a CT image, a CT diagnostic image that help the surgeon come up with a surgical plan on how they want to insert the needle to reach the target treatment area. And but for a surgeon to do this precisely, sometimes it takes a lot of experience and skill because the image uh, may not actually reflect what is happening in the environment in a timely fashion. So we need to come up with a system that is able to tell the robot how this can be done, and the robot can actually execute the surgical plan by the surgeon during actual uh, during the actual operation. So you see that there is also markers that the camera can take and recognize to understand and perceive the environment. So this is an important step as well to execute certain tasks. So planning is important, and vision as well as control is important. That is something that you will see as well in this course. So control is to help you to achieve the desired outcome, understanding what kind of input to give the robot, or the robot should actually, what kind of action the robot should actually do in order to achieve the right or desired um, outcome or output in a more engineering term. So this is a typical control scheme for robot. You have things like joint space, and of course it can be converted to the task space. Okay, and the observed parameters will be feedback to the controller to achieve the ideal outcome. So one example is a ultrasound image guided robot that actually take in information from the ultrasound. Okay, so uh, instead of having a human operator, the robot can actually take in ultrasound image and uh, position the probe to get the right image and help to do a needle insertion to achieve the treatment. So this is done, of course, by a human operator, which is a surgeon in this case. So the surgeon is doing this operation, but we can also have robot to execute this operation. But most of the time is to assist the surgeon, helping the surgeon to do certain steps. So in this case, the robot can actually stabilize the movement of the patient. So because the patient will be breathing, so the patient will be moving, it's very hard for the surgeon to send the needle to the right position by looking at the ultrasound and multitasking a lot of different things. They have to position the probe, look at the ultrasound image, and look at how the patient move, breathe, and insert a needle accordingly. Okay, and sometimes the needle will bend and things like that. So robot turns out to be a very good candidate in executing precisely what is planned, but responding to the environment, it requires some form of perception that comes from your ultrasound image. Okay, so if you look at this video, you will see that the video is probably going to do a better explanation than just telling you with some of the figures. So in this case, don't worry about the medical terms or the procedure. PCNL is basically the procedure in this case. And we want to send basically the catheter or the needle to the right position. So you see that this robot can actually be controlled by a human passively. Of course, cancelling out all the weight and of the heavy equipment. At the same time, listen to the operator's direction. So the operator can actually tell the robot where he thinks the tumor is roughly. So this, what you see here, is actually the on the right side. Let me get the pointer out. You will see this part here is actually a system trying to mimic the patient. So it's like a kidney, an artificial kidney that can be imaged by the ultrasound probe. So this is the ultrasound probe. And because the patient is breathing, so we have another machine to try to imitate this motion. So you will see that after a pre-scanning, this is like a patient breathing, and the robot is trying to follow the breathing of the patient by looking at the ultrasound. So at first you will see that it doesn't really track very nicely. The image is still moving. But as the robot starts to recognize and slowly control its position, it stabilizes the image. So it's like following the patient motion. And this end effector here is a needle inserting mechanism that will drive the needle down to the right position. So when the robot see that it's stabilized and it can find the needle, it will start to do the insertion, like what you see here. So for those who can see some white perturbation, this is actually the needle inserting towards the kidney stone. So now it's like acting on a patient that is not moving, but in fact the patient is moving. It is a robot that is helping to follow and track the patient motion so that the needle insertion can be done in a precise manner. Okay, so there are other examples in how we can use uh, vision to provide the robot with the perception so that it can control its motion in the environment and execute the task in the right manner so as to achieve the desired outcome. Okay, so this is something that we will go through again when we look at robot vision. Okay, basically it's a micro manipulator, a robotic micro manipulator that automatically bring the needle to the cell. Okay, of course, there are some videos that we have here to actually show you the process. But don't worry, this is just a very simple demo video, nothing intense. You will just see how the user can select the needle that he wants the robot to recognize and uh, manipulate. So in this case, to track this needle, and so the robot will actually move this needle according to the user's command as they do it on a 2D space. Okay, for those who are familiar with the camera model or computer vision photogrammetry actually, you will know that a 2D image is very hard for the robot to take only 2D image to do a 3D task, okay, to execute 3D path because 2D image only give you two-dimensional information. But in this case, in this research, there's actually a special way, a novel way of helping the robot to execute 3D motion based on just a 2D image of this microscope here. So this is one demo. The user first select the needle head. So as it is moving, the robot follow the command of the user. So you see all three axes of this robot is actually moving concurrently to execute a 2D specified path. But in real case, it is actually moving in 3D space because the robot is not mounted in parallel to the imaging plane. But don't worry, this can be a little bit technical just to let you know that we can use microscopic imaging technology to help manipulate this kind of micro robot to achieve motion or task in micro scale as well. And I believe this video is actually a very good example that show you how mechanics, control, and perception is demonstrated in a design robot by Boston Dynamics. I'm going to show you this video. Let me see if I can get the pointer to explain to you some of the process. You see a navigational map. So the robot need to know about the surrounding and the plan of with respect to the surrounding, how it should move. And there will be obstacle avoidance data. That means it is trying to perceive its surrounding. When there are obstacles, it will try to move away. You see, when it's climbing the stairs, there's a lot of dynamic involved that requires control. Because as a programmer, you can't possibly know how a robot should react to all kinds of information, all kinds of situation. You need some sensing and control capability. And in this case, you realize a robot is very smart to turn around when it's going down the stairs. So the head is facing upward because that is the better uh, position to go down the stairs for this kind of robot designed in this fashion. So there's a lot of planning and decision making in this case that you will see, a lot of control, a lot of dynamics, the kinematics to come out with the mechanism, the design of the mechanism, and computer vision to provide the perception of the environment and the planning of the navigational track, the path planning in the navigational map. Okay, so this kind of give a very quick overview of what you're going to learn in the next 15 weeks. And I will see you in the live streaming where we talk more about um, the spatial representation and transformation. That is the kinematic aspect of robotics. And we will of course use the example explained earlier on, and then go through the um, content in the live session on Monday and Wednesday. Okay, so with that, I'll see you in the live session. Thank you.